I want to say I signed up to this conference probably in the first 5 minutes of the pre-registration, whatever. I was very excited. Then I was invited to speak, and I'm so happy about it. So thank you to the organizers. I really wanted to come here because I grew up in the Technion, and that's how I feel mathematically. Micha taught me topology and algebraic topology, and then we continued some sort of learning, reading group. So that shaped the way I think. I think of algebraic topology in a very, geometric, topological kind of way. I try and do the simple arguments that Micha always does so easily. The most memorable moment, though, was that in class in topology one day, Micha goes, "Okay, I want to show you something." He wanted to, flip a belt around, but that was harrowing. Thanks. Anyway, thank you. Happy birthday. I will start talking about your math now. So let's talk about RAAGs. RAAGs are something between free groups and free abelian groups. Great, so you can ask what's the, QI classification of RAAGs. So every time you ask a question about RAAGs, you sanity check and ask free groups. They're, all QI to each other. Jesus, everything is finitely generated, okay? I'm always using the buttons. Free abelian groups are QI rigid. Let's say absolutely QI rigid. By that I mean not just in the class of RAAGs. Any group QI to Z to the n is commensurable, let's say, to Z to the n. Good, so these are the easy things, and now non-easy things. Berstuck and Neumann, Berstuck, Neumann showed that all tree RAAGs on trees, are QI to each other. Okay. Trees. That's because each RAAG on a tree is a graph manifold, and they showed all graph manifolds are QI to each other. I don't know if that's a because, but that's what they did.
Big enough tree?
No, any, yeah, okay. Any big enough tree, diameter greater than 3. Yeah. Then around the same time, maybe slightly later, Bestvina, Kleiner, and Sageev looked at two-dimensional atomic RAAGs. So they showed that atomic RAAGs are QI rigid amongst themselves. I will define atomic, don't worry. Gamma is atomic if it has no leaves. So we want to be furthest away from trees that we can. No cycles of length smaller than 5. That means 2 things. So a cycle can be of length 3 or 4 if it's smaller than 5. So it means it's two-dimensional. Largest flat is a 2 flat. And it, Adrien said this in his talk yesterday, doesn't contain F2 times F2. That's what having a 4 cycle means, both directions. Last thing, no separating closed star. And there's a very easy reason for that they observed. So what's the easiest graph satisfying 1 and 2, which has a separating closed star? It's doubling the 5 cycle. Okay, and that actually sits as an index 2 subgroup, so in particular it's QI, inside the 5 cycle RAAG. I wanna do something smart here. How can you see this easily? Danny, don't shout at me, please. A, B, I'm writing the generators. E is a generator, apologies. And now I do the following trick. Because I doubled along this vertex, it gets a power, A squared, and the other guys get a conjugate, C to the A, E to the A. What I wrote here is a homomorphism. It's defined on generators. You can check it's a homomorphism. You can check the kernel is, well, it's the kernel of a map to Z mod 2Z. Okay, good. Great. What happened next is that Jining started his PhD. Fast forward a bit, and was, as he said, generalized all of Sageev's work. He said it. Stop. Okay. That's on the mechanism. Okay. I have no idea what's written there anymore. But you do. So, Huang, in 2016, approximately, looked at RAAGs with finite outer automorphism group. Like these. These have finite outer automorphism group. This is something you can read from the defining graph. I will actually tell you in a second. So, A gamma 1, A gamma 2 have finite outer automorphism group, short for that. Then, if they are QI, then the graphs are equal. It's actually the same thing that's written there in other words. I just, for some reason, phrase it differently. Good, what's finite out? From the defining graph point of view, it's no link of W is inside star of V. In 2 dimensions, in that case, it's exactly no leaves. And no separating vertex star, something we've seen. When I say vertex star, I mean closed. It's kind of obvious in this context. Good. Yeah, Jining also showed other cases of rigidity and a smaller class of RAAGs are absolutely QI rigid amongst all groups. So if a group is QI to it, then it's commensurable to it. I want to talk about this, though. So idea of proof. Was to first show the following. Actually, this was in a different paper. for general RAAGs, if phi from a gamma 1 to a gamma 2 a qi, then there exists some constant depending only on the qi constants of phi, such that for every top dimensional flat in the domain RAAG, there exists a flat in the codomain RAAG, such that f is sent to a d distance, Hausdorff distance from f prime. So that was step 1. Step 2 is you need to upgrade that to standard flats, flats that are spanned by directions in the group. Upgrade to standard. Step 3, upgrade to standard geodesics. When you get it for standard geodesics, you get, BestvinaKleinerSageev didn't have this notion yet because Kim Coverta defined it in 2013, but they actually used it. You get an isomorphism of extension graphs, which I will talk about more towards the end of the talk, but now just bear with me. It's a graph you obtain from the defining graph. Gamma 2x. And here using, I think also before, but here using the graph properties, this implies that gamma 1 is equal gamma 2. This is not true for all graphs. Great. That's the idea. Everybody here, or at least 4 people here, know this a lot better than me, so you can ask them later. Okay. We asked ourselves, I think that's what I'm supposed to say now. Yeah. What about QI embeddings? So in their proof, even in the first statement, they use strongly the existence of an inverse. In BestvinaKleinerSageev, they have some poset, and they get some isomorphism between the poset by using the QI and then the QI inverse. In Huang, it's similar in a way. So what do you lose? What do you still have when you just restrict to embeddings? We actually started by looking at embeddings into products of trees that Harry talked about. So I will not talk about trees here. But what we ended up doing is telling people in the last year that our paper is going to come out in the next few days. It came out maybe last week. Okay, good. Anyway, our theorem. In 2 dimensions, we can say the most. So gamma is triangle free. And the diameter of gamma, this is a necessary condition, is greater than 2. Let's just say connected, but you can just say any connected component. Y is a proper finite dimensional CAD0 cube complex of asymptotic rank 2. You should think square complex, okay? Then, if I have a QI embedding of the RAAG on gamma into Y, there exists a constant such that the same conclusion for every f, there exists f prime with the Hausdorff distance of the image of f from f prime being finite. And in the case y is two-dimensional, the constant depends on the qi constants, and that's it. Singular two flats. Anyway. Good. It is, the diameter is important because Brian Bowditch has an example where this does not hold for embedding 3 times r into 3 times 3. In higher dimensions, I will tell you after the proof, maybe. I'm going to give you the full proof. No, I'm going to give you an idea. Okay. Great. That was great. Idea. So we first show this for flats that have this type of branching. So some of the flats, all flats have these orthogonal directions, and some of them, in a sense most of them, have flats coming off of those directions. Right, this is one direction, this is a horrible, horrible picture. Neil would be disappointed. Okay, it is not better now. And I also want flats branching out in the other perpendicular direction. Great. So this, for example, is a flat corresponding to this edge in the defining graph. I know people in the back can see, but I don't know what to do about that. Great. So now what happens? Now we use Huang's result, actually Brian Bowditch's result, but I don't want to say asymptotic cone, to say that the image of the white flat is close to a union of orthons. 1, 2, 3, that's not good then. I mean, that is good. Let's say it's 5. So it's 90 degrees here, right? I hope this makes sense to you. Great. And now these lines, the white lines I drew, are intersection of the images of 2 flats. So pink, I don't know where it goes, but it also goes to a union of orthons, and it intersects this thing in the one skeleton. So this yellow, which it looks to you like white, goes to something in the one skeleton. I claim it goes to a geodesic. If it does not, it goes in a 90-degree angle, and then the geodesic perpendicular to it doesn't have where to go. Okay? As imagined by Lifshitz, imagine things are continuous. So it has to go to a geodesic. But then parallels of yellow should cover. And that can only happen if I have a 2 flat. That's the idea for branching flats. The only other option, if a flat isn't branching, is apparently if it's a standard leaf flat. In that case, one of the geodesics, because of the diameter assumption, comes from a flat that is branching, and so must go to one geodesic, and then parallels of it should cover. So it goes to a 2 flat. Excellent timing. You didn't understand, but I'm on time. What's happening in higher dimensions? Any questions? You can understand today. So I stated this theorem in 2 dimensions. We actually have a corresponding theorem for higher dimensional RAAGs, and then I take Y to be a cube complex of the same asymptotic rank as the RAAG I started from. Why am I stuck? What did I want to say? I don't remember. Anyway, what are the assumptions there? I would need to mimic this sufficiently branching. So I'd use flats that are spanned by branching condition, by branching geodesics. Works for flats spanned by something we call branch complemented geodesics. And this is a defining graph of a RAAG, a 3-dimensional RAAG, and this corresponds to a branch complemented geodesic. So I want the geodesic to be the intersection of maximal dimension flats. I'm talking about, this is a defining graph of the RAAG, and so a vertex corresponds to a geodesic in the Cayley graph, yeah, in the universal cover of the Soveti complex. So this is branching, it's the intersection of 2 flats, and this is a codimension 1 complement, and it is also branching. And that's what I want all my geodesics to be like. So for example, just going to repeat this picture 3 times. The middle flat is sufficiently, we have a different name for it, but it's sufficiently branched. And in general, those are the flats that would go to close to flats. Cool. Questions? Time? Good. Right. I forgot to say something. It's so high up. It's okay, I'll say it later. What do we get from this? We get that if also, so if a RAAG is sufficiently branched, meaning all of the standard flats are like this, or all of the standard geodesics are branch complemented, then and lambda is, say, square free, such that I always want to assume the dimension of A gamma, of the RAAG and gamma, and the dimension of the RAAG and lambda are the same. This is something, by the way, that you get for free if you assume a QI, but you just don't have that if you assume QI embedding. Then any QI embedding between these 2 RAAGs maps standard geodesics to standard geodesics. Up to Hausdorff distance, okay? So now this is suspiciously similar to what they get in the proof of their QI rigidity. So you can ask yourself, do we have some sort of QI embedding rigidity? And the answers are yes and no. This is just the end of that. So as in step 3, BestvinaKleinerSageev and Huang get that the extension graphs are isomorphic, we get that they combinatorially embed. I can write it there where you can't see. This means gamma x combinatorially embeds. Good, good, good. My hand is happy. Combinatorially embeds in lambda x. I didn't define extension graph, and I will when I need to, depending on time, because maybe I won't need to. And combinatorially embeds means the image isn't necessarily an induced subgraph, but vertices go to vertices, edges go to edges. Excellent. So rigidity that we do have, it is a theorem, but it definitely needs that theorem, is that if f2 to the n times a c5 to the m qi embeds in some RAAG of the same dimension, which is n plus 2m, right? C5 is the cycle on 5. It's what I drew up there, middle, maybe. So it's a dimension 2 RAAG, and the free group is dimension 1. Anyway, if it embeds, qi embeds, then you can find it as a parabolic subgroup. Parabolic means that you can see it from the defining graph. Actually, the defining graph of this RAAG, which is the n-partite graph on two vertices, join with m join of C5, which is why I didn't write that, is an induced subgraph of lambda. So you get rigidity. For bigger cycles, you get a version of rigidity, but maybe the size of the cycle will go down. So I can't promise you that if you started with C7s, you can get C7s, but maybe you'll get C5s. But you won't get something smaller than C5. Good. I still can use this. In BestvinaKleinerSageev, they point out that their qi rigidity that's above me is surprising maybe because the qi group of these atomic RAAGs is actually very, very big. And that is true. They prove it. And, and this is opposed to many other qi rigid groups where their qi group is exactly the group, like mapping class group. We classify this qi group for the absolutely qi rigid RAAGs. Classification of qi. I mean, I can tell you the structure of each qi of A gamma. That's what this sentence should mean, where A gamma is absolutely qi rigid. This is, as I said, a subclass of the finite out RAAGs, and they have another condition, which is also a condition that can be read from the graph. And this is exactly because we prove things using the extension graph, or at least that's why we need that. I'm not sure why Ginny needs that. Good. And we do the same for the QIE group, so embeddings, self-QI embeddings of cycle RAAGs. Cn. I don't know how many. That's it. For n greater or equal. Good, 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 good. Excellent. So good, I'm so good. Okay, so I talked about rigidity, But actually not everything is perfect. We get only a combinatorial embedding of extension graphs. So the answer to the general question that you may thought of maybe a QI embedding implies some sort of virtually subgroup, the answer is no to that question that I made up right now. Let me talk about the extension graph for that. Kim Coberta in 2013 studied a lot of RAAGs, subgroups of RAAGs, and they can tell you exactly when a two-dimensional RAAG is a subgroup, which RAAGs are subgroups of two-dimensional RAAGs. They can read it off the defining graph. And they used this thing they called extension graph. I'm going to give 3 definitions to it. It's a graph. Vertices are standard geodesics up to parallelism, and edges if they span a 2-flat. Okay, that's maybe if you don't have a good imagination, you'll be happier with the following definition. What's a standard geodesic? It's something labeled by S, with some base point. What's parallelism? Well, commutation. So the vertex set can also just be S to the G, where S is a generator and G is some element. And spanning a 2-flat is exactly commutation. This word is commutation. Okay, 3rd definition, you just construct it. You start with your graph, and then you double along a vertex star, like the picture above us. And you label it like the picture above us in order to get all of this set. So if I start with A, B, C, D, E, then these are conjugates by A. I will have another copy, conjugates by A squared, and I can keep on doubling, putting more and more copies of the 5 cycle in this example. And I'll get everything. Perfect, good, everybody's happy. So Kim and Coberta proved that I heard a lot of compliments to people who, when they finished the talk, exactly finished the boards. I want to let you know, I also give good talks. So they use their results. They have more than what I'm just saying, but in particular, they can tell you exactly when to cycle RAAGs. One is a subgroup of the other. ACM is a subgroup of ACN. Say 4. Okay. If and only if M is N, or M is N plus P N minus 4 for some P. This is exactly because there's actually a secret if and only if there, which is if and only if CM extension graph is induced in CN extension graph. Right. So now we have, which we first tried to prove that the only way to get a combinatorially embedded CM extension graph in CN extension graph is if it's induced. That's wrong. And by doing that, we constructed QI embeddings. So by understanding it's wrong, that's doing that. ACM QI embeds in ACN for n greater or equal to 4, I think. If and only if 5. If and only if something weird is happening with 4. It's a theorem Harry mentioned. Okay, you remember. If and only if m equals n or m equals n plus p n minus 4 plus q n minus 2, where p is greater or equal to 1 and q can also be 0. When q is 0, it's induced. Because what's happening? Where does the n minus 4 come from? It comes from this. It's exactly the boundary circle in the picture above after we doubled. So if you can see, that is length 6, which is 5 plus 5 minus 4. But you can also get n minus 2 because you can take conjugates by 2 neighbors. So I can look at A, B, C, D, E. I know it's backwards this time. And I can double by A, and then I can double by B. And I'll get these guys. This would be E to the AB. D, that's the letter that's over there, to the AB, and C to the AB. So together, I get n plus n minus 2 around, which isn't perfect because I actually need to do an actual double. I will need to get 1 n minus 4 in order to be able to construct a QI embedding. So as with Kim-Coverta, the idea was that this is if and only if there's a combinatorial embedding of extension graphs. I think my time is up.